So in this new chapter, we will investigate the convergence of functions. So today I will introduce three types of different convergences, and I will examine each one. So let me say that we will be working here in a space omega with a sigma algebra F and a measure mu. So I will assume that the space is, so omega, it's a sigma finite with respect to mu, of course. And I will also assume that the sigma algebra F it's sigma complete. So remember that since F it's sigma complete, if I have a function F defined in omega and taking values in R bar, which is F measurable, and if I have another function G defined in the same space such that G equal to F almost surely, then G it's also F measurable, because we are assuming that F it's complete with respect to the measure mu. So I can define, in view of this fact, an equivalence relation, which I will represent by that symbol. So I'll say that two functions f and g are equivalent if the measure of the points x such that f is different from g, it's equal to 0. So I leave it to you to check that this is an equivalence relation. Well, it's clear because, well, f is certainly equivalent to f, and if f is equivalent to g and g equivalent to h, it's very simple to show that f is equivalent to h. So this is an equivalence relation. And therefore, if I represent by M the space of functions which are measurable with respect to f, so this is the class of functions f from omega to R bar which are f measurable. So this is a space of functions, and I can just define as mu, a calligraphic mu, M, as the space M modulo this equivalence relation. So now in this space M, functions are in fact representative of the equivalence class. So I will be essentially working in this space. So whenever I'm talking about a function, in fact, I will be talking about an equivalence class. This function will be a representative of this equivalence class. So this is the background that we will assume throughout this chapter. So we will be talking about three different types of convergence. The first one will be, well, I will define it later, a sequence fn converging to f almost everywhere. That will be our first definition or type of convergence. Then we will be talking about uniform convergence almost everywhere. And finally, almost uniform convergence. So let's start with the first one, which is convergence almost everywhere. For that, let me just remind you what is pointwise convergence. So this is, say, 1a. Pointwise convergence. So if I have a sequence of functions fn defined on a set E and taking values in R bar, and a function f also defined on E and taking values on R bar, I will say that fn converge to f pointwise if for all x in E, fn of x converge to f of x. So this is very simple. If you want to check that sequence fn converge to f pointwisely, well, you just have to check that the sequence of extended real numbers fnx converge to fx for any point x in E. So with this in mind, we will now define almost sure convergence. So this is 1b, which is almost sure convergence. So I'll say now that I have a sequence of functions fn and a function f defined in omega and taking values in R bar. And I will say that fn converge to f almost surely or almost everywhere. So sometimes this is represented by as, sometimes it is represented by ae. Well, if, so this is a definition, if there exists a set E which is f measurable such that, well, the first requirement is that the complement of E has measure 0, and then the second requirement is that on the set E, fn converge to f pointwisely. So fn converge to f pointwisely. On E. Which means, as we have seen, that fn of x converge to fx for all x in E. So almost sure convergence means that, well, except from a set of measure 0, you have pointwise convergence of fnx to fx. So this is the definition, and we now will examine some properties of this almost sure convergence. What's important here is to note that this notion of convergence is in fact convergence in the equivalent class. What do I mean by that? I mean the following. Well, let's assume that fn converge to f almost surely. And let's assume that, well, let's take another function in this equivalent class of fn. So let me take another function gn, which is equivalent to f, and a function g, which is equivalent to f. What I claim is that gn converge to g also almost surely. And this is clear, so let's prove that. That's very simple. Well, since fn converge to f almost surely, we know that there exists a set E such that mu of E complement is equal to 0, and such that fnx converge to fx for all x in E. So this is just the definition of almost sure convergence of fn to f. Now, when we say that fn is equivalent to gn, this means that there exists a set, let's call it fn, which is also an element of the sigma algebra. Here I forgot to write that E is an element of the sigma algebra so that we can make sense of the measure of the complement of E. So here, saying that fn is equivalent to gn means that there exists a set fn in F such that the measure of fn complement is 0, and such that fn of x is equal to gn of x for all x in fn. In the same way, saying that G is equivalent to F means that there exists a set F in the sigma algebra F such that the measure of F complement is 0 and such that Fx is equal to Gx for all x in F. Okay. So now let's define the set H. H will be just the intersection of all these sets. So H will be E intersection F intersection the intersection over all n larger than 1 of the set Fn. What I claim is that on the one hand the measure of the complement of H is 0. First, observe that H it's an element of the sigma algebra F because if each of these sets E, F and Fn is an element of F. So H it's clearly an element of the sigma algebra F. And I claim that the measure of the complement of H is 0. Well, the complement of H is, by its definition, the complement of E union the complement of F union the complements of Fn. So this is E complement union F complement union the union of n larger than 1 of the complements of Fn. And the measure of this union it's less or equal than the sum of the measures of each of these sets, and the measure of each of these sets is 0, so this measure it's less than or equal to 0, which means that the measure of the complement of H it's equal to 0. On the other hand, let's complete the proof in this space. What I claim is that if X belongs to H, then Gn of X converge to G of X. Well, and why this is true? Because since X belongs to H, X belongs to Fn for all n. And on the set Fn, Gn is equal to Fn. So on this set H, Gn is equal to Fnx. On the set E, Fnx it's converging to Fx, but H it's contained on E. So Fnx converge to Fx. And on the set F, Fx it's equal to Gx. And since H is contained in F, we have this identity, which means that G and X converge indeed to Gx. So we proved the existence of a set H in the sigma algebra, such that the measure of the complement of H is equal to 0, and such that on H, G and X converge to G of X. And this means that Gn it's indeed converging to G almost surely. So we proved that if Fn, so that this property of almost sure convergence, it's a property of the equivalent classes. Because if we know that a sequence Fn converges to F almost surely, we can change the functions which represent the equivalent classes and obtain that we still have that Gn converges to G almost surely. So a second property is the following. Well, assume that Fn converge almost surely to a function f, and that it also converge almost surely to a function g. So what I claim is that this implies that f is equal to g almost surely. And we can prove that exactly in the same way, which means that if we know that Fn converges to f almost surely, this means that there exists a set E such that in the sigma algebra F, such that mu of E complement is 0, and Fn of x it's equal to converge to f of x for all x in E. By the same reasons, since Fn is converging to G almost surely, there exists a set F in the sigma algebra F such that mu of F complement it's equal to 0, and such that Fn of x converge to G of x for all x in F. So, if we take H as the set E intersection F, we have that on the one hand, mu of H complement it's equal to 0, because the complement of H is the union of these complements, and both of them have 0 measure. On the other hand, if x belongs to H, G of x is the limit of f and x, but the limit of f and x it's also equal to f of x. And this means that for all points x in H, G of x is equal to f of x. And since the measure of the complement of H is 0, this means that G it's almost surely equal to f, or in other words, that G it's equivalent to f. And this is exactly what we wanted to prove. So if the same sequence of functions is converging to two different functions almost surely, these two functions, these two limits are equal almost surely. So let me conclude with an example. Let's consider the interval 0, 1. On this interval 0, 1, let L denote the Lebesgue sigma algebra of subsets of 0, 1, and lambda denote the Lebesgue measure on 0, 1, which is defined on this sigma algebra of the Lebesgue cells. And remember that this sigma algebra is indeed complete. And lambda it's finite, so of course lambda it's sigma finite. So now let me consider the following functions. Fn of x it's equal to x to the power n. So let me draw here the graph of this function. So at 1 it's always equal to 1, and for any x smaller than 1, this sequence is converging to 0, so it typically looks like that, and this sequence is converging to 0 as n goes to infinity. So it's clear that Fn of x converge to 0 for any x in 0, 1, but Fn of 1, which is equal to 1, is not converging to 0. So here is an example. So we have here a set whose complement it's the point 1, which has Lebesgue measure equal to 0. And in this set, we have pointwise convergence. So it's true that Fn converge to f lambda almost surely, so Lebesgue almost surely, where Fn it's this function x to the power n, and the function f of x it's equal to 0 for all x. But it's not true that Fn converge pointwisely to the function f, because at 1 the sequence Fn1 does not converge to 0. So you have here a very simple example of a sequence of functions which do not converge pointwisely, but which converge almost surely with respect to the Lebesgue measure. Now, I'll introduce the second type of convergence, which is the almost uniform convergence, or uniform convergence almost everywhere. So let me write that. So this is the uniform convergence almost everywhere. So before introducing that, let me remind you what we understand by uniform convergence. So let's assume that we have a set E, and we have a function f and a sequence of functions fn, which are defined on E and are taking value in the extended line. So we'll say that fn converge to f uniformly if for any epsilon positive we can find an integer n, 0 and not, such that if n is larger than n naught, then fnx minus fx, it's bounded by epsilon, and this for all x in E, or another way in saying that this holds for all x in E is that the supremum for x in E of this difference is bounded by E. So what's important here is that we can find an integer n naught for which this distance is bounded by epsilon uniformly over all points of x. So this is what we understand by uniform convergence. The fact that you can choose one integer n 0 for which this difference is bounded uniformly over all points over E. So based on that, I will introduce the concept of uniform convergence almost everywhere. So uniform convergence almost everywhere is very similar, but the uniform convergence will not happen in the set omega, but only in a subset which has whose measure has total measure. So let me be more precise. So this is a definition. So again, assume that you have measurable functions f and fn, which are defined on omega and taking value in R bar. I will say that fn converge to f uniformly almost everywhere if I can find a set E on the sigma algebra F such that, well, mu of E complement it's equal to 0. So we have a set E. The complement of this set E has measure 0, and Fn converge to F uniformly on E. Which means that if we restrict these functions to the set E, we have uniform convergence. So this is a definition, and we will now investigate some properties of this convergence. So for that, I will introduce the idea of essential soup of a function. So assume that I have a function f defined on omega, taking value on the extended line, and assume that there exists a positive such that the measure of the points x such that f it's larger than a, that this is 0. Okay, assume that there exists some a which has this property. Well, if this happens, then I can find the smallest a which has this property. So, and this will be the essential soup of my function f. So the essential soup of my function f will be the smallest a, the infimum, over all a positive, such that the measure of the points x such that fx is larger than a, it's equal to 0. Right? So it's clear that if mu of these points a it's equal to 0, and if I take b larger than a, it's clear that the measure of points x such that f is larger than b, it's equal to 0, right? Because, well, since b is larger than a, if f is larger than b, since b is larger than a, f it's also larger than a. So this set, it's contained in the set in which f is larger than a, which has measure 0, and therefore this set has measures 0 also. So in the line, you started at a point a in which this set has measure 0, so you know that for all b larger than a, all these sets have measure 0, and now you take the smallest a which has this property, and this is exactly our definition of the essential supremum of f. So this is, well, just remember that supremum of a function f is just, well, the supremum over fx for all x in omega. Well, and it's clear that the essential supremum of f, it's smaller than the supremum of f. Right? You can take, let's say, and this inequality can be strict. So like give you a very simple example. Let's take the line. Let's consider a function f, which is equal to 1, say, everywhere, but at the origin, it takes the value, say, 2 or plus infinity. So it's clear that if you are taking r with the Lebesgue measure, then if you take any a larger than 1, the measure of this set, it's equal to 0. So if a it's larger than 1, and you take the measure of all points x such that fx it's larger than a, well, this set corresponds to the origin, and the measure, the Lebesgue measure of the origin is 0. So for any a larger than 1, this set has measure 0, while for a smaller than 1, if you take a now smaller than 1, you take the measure of all points x such that fx it's larger than a, well, this is the old set R, so this measure will be plus infinity. So you have a jump, so this function as a function of a has a jump at 1. For a smaller than 1, it takes the value plus infinity. For a larger than 1, it takes the value 0. So in this example, the essential supremum of f, it's 1. Well, but the supremum of f In this example, it's 2, or can be equal to plus infinity. So we have here an example in which the essential supremum of a function is really smaller than its supremum. In fact, here we are allowing to remove points which from a set which has measure 0. So this is why this is called the essential supremum, because we are allowed to remove points of sets in which we take the supremum if this set has measure 0. So now what I want to prove is the following observation. Let me call the essential supremum of f. Let me give a name to that. Let's say that this is C. And what I claim is that the measure of the points x such that f of x is larger than C, that this is equal to 0. Okay? So if I call by C the essential supremum of a function, what I'm claiming is that the measure of the points x for which f of x is larger than this value, that this set has measure 0. And the proof of that, it's very simple. Well, what I claim is that for all n larger than 1, the measure of the points x such that f of x is larger than C plus 1 over n, then this is 0. And this is correct because C, it's the essential supremum. And the essential supremum is the infimum over all A for which this measure is 0. So if this measure were positive, if the measure of this set were positive, then C could not be the infimum. We would have to look an infimum larger than C plus 1 over n. Right? So if what I'm saying is that if this set had a measure, a strictly positive measure, then C could not be the infimum of all A for which the measure of this set is equal to 0. Now, if you accept that this set has measure 0, we can conclude that this set has measure 0 because if this is true for all n, it's also true for the union. So the measure of the union of all n larger than 1 of the points x such that f of x is larger than C plus 1 over n. Well, since the measure of each set is equal to 0, the measure of the union is also equal to 0. Well, but this set, it's exactly that set, right? First of all, observe that this set is contained in that one. To show that this union is contained, I have to show that each set is contained. But this is easy because, well, if fx is larger than C plus 1 over n, then it's also larger than C. So each set here is contained here, and therefore the union is also contained. So it's clear that this set is contained on that one. This union is contained on this set. On the other hand, I claim that this set is contained in that one. And this is true because take a point in this set. If I take a point in this set, this means that the absolute value of fx is larger than C. But if it's larger than C, strictly larger than C, it has to be strictly larger than C plus 1 over n for some n. So this point will be contained in one of these sets and therefore in the union. And this proves that this set is contained in this union and therefore they are equal. we prove that the measure of this set is equal to 0, and therefore the measure of this set is equal to 0. So we just proved that if you take the essential supremum of a function and you consider all points for which fx takes a value larger than this essential supremum, then this set has measure 0. Observe that it's, of course, if I change here the strictly inequality by an inequality, then it's not true anymore, and our example shows that, because we have seen that the essential supremum of this function is 1. So if I now compute the measure, the Lebesgue measure of all points x such that that function is larger or equal than 1, well, I get plus infinity. So here the strict inequality is very important. So this is first property. So what we proved here, we introduced the concept of the essential supremum, and we showed that this fact, right, that the measure of this set, well, if I take here C as the essential supremum, that the measure of this set is equal to 0. So now we'll see further properties of the essential supremum. So the second property I want to show is that the essential supremum, it's a class property. In the sense that if I take two functions f and g which are equivalent, then the essential supremum of f, it's equal to the essential supremum of g. And that's very easy. So assume that f is equivalent to g. This means that I can find a set E in f such that mu of E complement it's equal to 0, and f it's equal to g on E. Now let's consider the set of points x such that g of x it's larger than c, where I will take here a c as the essential supremum of f. So let's call the essential supremum of f c, and let's estimate the measure of this set. Well, now I will intersect this set. So I'm estimating this measure. I will intersect this set with E and the complement of E. Well, the complement of E, so let's call, let me explain what I'm doing. Let me call A this set. And what I'm doing here is that I'm saying that mu of A, it's less than mu of A intersection E complement plus mu of A intersection E. Right? E complement has measure 0, so this set here, it's bounded by mu of E complement, and which is 0. So, in fact, mu of A, it's bounded by mu of A intersection E. But on the set E, f is equal to g, so I can replace g by f. So, by that inequality, the measure of this set is smaller or equal than the set x, such that f of x it's larger than c. Intersection E, but now I can just forget the set E and bound mu of A intersection E by mu of E, mu of A. So let me insist or explain again what we did here. I call that set A. I intersect A with E complement and E. With E complement, I estimated this piece by 0. And then on A intersection E, well, since on the set E, F coincides with G, I replaced G of X by F of X. So I obtained this bound, and then I further bound this measure by the measure of the first set. So I just erased the set E. And once I arrived at that point, since C is the essential supremum of F, by the first property of the essential supremum we proved, this set it's equal to 0. So we proved that the measure of all points x such that g of x is larger than c, it's equal to 0, which means that the infimum over all a is less or equal than c. So this implies the infimum is the essential sup of G. So since the measure of this set is equal to 0, the infimum over all A such that the measure of this set with A in place of C is equal to 0, this infimum should be smaller than C. But C is equal to the essential supremum of F. So this proves that the essential supremum of G is less than or equal to the essential supremum of F. Well, now we can replace F by G, since the roles of F and G are absolutely symmetric, to get the reversed inequality and prove that they are in fact equal as we claimed. So the essential supremum, it's a class property. If you take two functions in the same class, their essential supremums are equal. Now I claim that we can introduce a distance by using the essential supremum. So I'll take f and g, two functions, and I will define d of f and g as the essential supremum of f minus g. And I claim that this defines a distance. Fine. Well, of course, D is symmetric. In our definition of the essential supremum, we have a symmetry. So let me prove that if D f g is equal to 0, then f is equal to g almost surely. So which means that f is equivalent to g, and of course this distance, as we are seeing now, it's defined on the equivalent classes. Right? You can have two functions, as in our example, which are equal everywhere but in a point, and their difference will be equal to 0 unless in a point, and therefore the essential supremum will be 0, though they are different. So here we are claiming that this is a distance in the set of the equivalent classes. So in order to prove that f equal to g almost surely, what we have to show is that, well, if I have a function h whose essential supremum is equal to 0, then h is equal to 0 almost surely. Well, but this is very simple because, well, if the essential supremum of h is equal to 0, this means that the measure of all points x such that hx is larger than 1 over n, well, it has to be 0, because the infimum of this expression is attained at 0. Therefore, for any number larger than 0, the measure of this set has to be equal to 0. And if the measure of this set is equal to 0, the measure of the union, it's also equal to 0. And we have already seen that this union is in fact the set of points x such that hx is larger than 0. So this set has measure 0, and this shows that h is equal to 0 almost surely, and therefore that one of the properties of the distance is fulfilled, which means that if the distance of f and g is 0, then f is equal to g. They belong to the same equivalent classes. So this is a first property. So we have seen that the distance is symmetric, that the distance being equal to 0 means that the functions are equal. It remains to prove the triangle inequality. So to show that the distance between f and h is less or equal than the distance between f and g plus the distance between g and h. So let me consider. So this is an infimum. So let me call this, let's say, A, and this B, and let me consider the sets of points x such that fx minus hx is larger than a plus b. And I want to show that this set has measure 0. Right? A, remember, it's the essential supremum of f minus g, and b, it's the essential supremum of g minus h. Well, by the triangle inequality, we know that fx minus hx it's less or equal than fx minus gx plus gx minus hx. So if fx minus hx is larger than a plus b, then either fx minus gx is larger than a, or gx minus hx it's larger than b, right? Because if fx minus gx was less than or equal to a, and gx minus hx was less or equal than b, then this difference would be less than or equal to a plus b. But we know it's larger than a plus b. Okay? So either this one it's larger than a, or that one it's larger than b. Which means that the measure of this set it's less than or equal to the measure of the set x such that fx minus gx it's larger than a, or the measure of x such that gx minus hx it's larger than b. Right? If this happens, either this happens or that happens. Well, but now remember, A is the essential supremum of f minus g. And the first property showed that if A is the essential supremum of f minus g, then the measure of this set is equal to 0. In the same way, B is the essential supremum of g minus h, and we proved, therefore, that the measure of this set is equal to 0. So, the measure of this set is equal to 0. If the measure of this set is equal to 0, this means that the essential supremum of f minus h it's less or equal than a plus b. The infimum has to be less or equal than a plus b, because at a plus b the measure is 0. Well, but the essential supremum of f minus h, it's exactly the distance between f and h. And A is this distance, B is that distance, so this proves that this triangle inequality as we claimed. So now, fourth property is that, well, let's go back to the convergence. What we claim is that Fn converges to F uniformly almost everywhere if and only if the distance between Fn and F goes to 0. So what we did is that once we prove that, we will have the fact that the topology induced by this convergence is metrizable, which means that there exists a metric such that, well, the convergence happens if and only if the distance goes to 0. So we introduce the distance which corresponds to the topology induced by this convergence. And so let's prove that. So let's first prove that if you have a sequence converging uniformly almost everywhere, then the distance goes to 0. Well, that's very easy. Remember what we understand by uniform almost everywhere. This means that there exists a set E in the sigma algebra such that mu of E complement is equal to 0 and Fn converge to F uniformly on E. Well, that's fine. So now let's prove that the distance between Fn and F goes to 0. In order to prove that, we fix an epsilon, and we want to show that there exists n0 such that if n is larger than n0, then the distance between Fn and F is smaller than epsilon. So let me just remind that this is the essential supremum of Fn minus F, and we have to show that this is smaller or equal than epsilon. Well, so let's use what we know. We know that Fn converges to F uniformly. So for that epsilon fixed, we can find n0 such that the supremum of x in E of Fnx minus Fx, that this is smaller than E, epsilon, because Fn is converging to F uniformly on E, which means that given any epsilon, we can find this n0 such that for all n larger or equal than n0, this supremum is bounded by epsilon. But now, if I take such n larger than n0, and I want to estimate the measure of the points x such that Fnx minus Fx it's larger than epsilon, well, on the set E, Fnx minus Fx it's less than or equal to epsilon. Therefore, this set it's contained on E complement, and E complement has measure 0. So this set has a measure 0. So let me repeat. This set, I claim, it's contained on E complement, because on the set E, this supremum it's bounded by epsilon. Therefore, this set it's contained on E complement. Since E complement has measure 0, this set has also measure 0. If this set has measure 0, this means that the essential supremum of Fn minus f should be less than or equal to epsilon, because the essential supremum is the infimum over all A which satisfy that inequality. So this proves that the essential supremum of Fn minus f it's less or equal than epsilon, and this is exactly the distance. So we proved that the distance between Fn and f is converging to 0. So now we have to show the converts. Right, so now let's assume that the distance between Fn and f goes to 0. So this means that the essential supremum of Fn minus f goes to 0. Which means that for any epsilon, I can find n0 such that if n is larger than n0, then the essential supremum of Fn minus f it's less than epsilon. But the fact that the essential supremum of Fn minus f smaller than 0 means that the measure of the x such that Fnx minus fx larger than epsilon, that this has to be equal to 0. Because, well, we have seen that this inequality holds if I replace here epsilon by this essential supremum, but since epsilon is larger or equal than the essential supremum, it has to hold also for epsilon. So what we know is that for any epsilon, I can find n0 such that if n is larger or equal than n0, then the measure of this set is equal to 0. So with that set, I will construct the set E. So remember here I need to construct a set E in which this convergence is uniform on E, and E complement has measure 0. So let's construct this set. Let me take k larger than 1, and let me consider A to be, say, epsilon 1 over 2k. Let's be safe and take epsilon equal to 1 over 2k. So I know that there exists nk such that if n is larger than nk, then the measure of the points x such that Fn x minus fx larger than 1 over 2k, that this is equal to 0. So for all n larger than n0, this set it's equal to 0. The measure of this set it's equal to 0. Therefore, I can take the union here. So the measure of the union of all n larger than nk, right? Now n depends on this set has measure 0, provided n is larger than nk. So I take the union over all n larger than nk of the sets x such that Fnx minus fx it's larger than 1 over 2k, and this is 0. And this is true for all k. So now I can take the union over all k. So since this holds for all k, I can take here, well, no. So let me erase these two lines. And let me take the union over all k here. Since this set is equal to 0, the measure of this set is equal to 0, I can take the union. So I conclude that the measure of the union over all k larger or equal to 1, the union over all n larger than nk of the x such that f and x minus fx it's larger than 1 over 2k, that this set has measure 0. Okay. And this is our set E complement. So this set, it's of course in the sigma algebra, and we just proved, well, by definition, this set E complement has measure equal to 0. So to complete the proof that Fn is converging to F uniformly almost everywhere, I have to show that on the complement of this set, I have uniform convergence. So I will erase what I wrote and I will conclude the proof. So let me first write what is the set E, and let's remember that I have to show that Fn converges to F uniformly on this set E. So what is the set E? Here's E complement, so I just need to take the complement of this set, and when I take the complement of this set, I get the intersection over all k, the intersection over all n larger than nk, of the complement of this set, but the complement of this set is the set of points x such that fnx minus fx it's less or equal than 1 over 2k. So this is my set E, and now I need to prove that Fn converges to F uniformly on E. Well, that should be easy to check. So to prove that, let's fix some epsilon positive, and I need to find one n0 such that for all n larger than n0 and for all x in E, this difference is bounded by epsilon. So 1 over 2k, it's converging to 0, so there exists a k0 such that 1 over 2k 0 it's smaller than epsilon. Once you found this k0, associated to that k0 there is nk0. So let's consider a point n larger than nk0. Well, if n is larger than nk0, and I take x so let's consider x in E. Since x is in E, it's contained in this intersection. So in particular, it belongs to this set in which I have k0 here fixed. So it belongs to this intersection over all n larger than nk0. And this means that since it belongs to this intersection, this means that for all such n, f and x minus fx, it's bounded by 1 over 2k0, right? Let me just explain again. Since I consider a point x in E, since it belongs to E, it belongs to this intersection, which means that it belongs to the set with k0 fixed. So let's replace here k by k0. So we know that x belongs to this intersection. What does that mean, that x belongs to this intersection? It means that for all x belongs to this set for all n larger than nk. So if I take n larger than nk0, x belongs to this set, which means that fnx minus fx, it's smaller than 1 over 2k0, and we chose k0 such that this is bounded by epsilon. So this is true for any x in E. It's true that this difference is bounded by epsilon. So the supremum for all x in E of this difference is bounded by epsilon, and this proves that Fn is converging to F uniformly on the set E, which proves the converse claim. So we just proved that this distance corresponds to the topology induced by this uniform convergence almost everywhere. In other words, that a sequence converges uniformly almost everywhere if and only if the distance converges to 0, and this was our fourth claim. So let me conclude this section with two remarks. So the first one is the following. Let's call L infinity the space of all functions f in M. So remember, this calligraphical M represents all the functions, this equivalence class of functions. So I'm taking all equivalence classes such that the essential supremum of f is bounded. We have seen that the essential supremum, it's a property of the class. So this is well defined. If I take two different elements here, their essential supremum are the same. And the remark is that this space L infinity, it's linear. So, and I leave to you to check that. Linear in the sense that if I take a function f in L infinity and say another function g in L infinity, and if I take a number alpha in R, what I claim is that alpha f plus g is an element of L infinity. Right? And this is, well, the supremum essential. So what you have to show is that the supremum essential, this essential supremum of alpha times f, it's equal to alpha times the essential supremum of f. And we have seen already when we proved that d was this distance, is that the essential supremum of the sum of a sum, it's bounded by the sum of the essential supremums. So this proves that L infinity is a linear space. So this is my first remark. And my second remark, well, it's not a remark, it's an example. The same example, actually. So let's recall that the example I gave. So the interval 0, 1, the Lebesgue measure, and the Lebesgue sigma algebra, and the functions fn of x given by x to the power n. And now what I claim is that it's not true that fn converges to f uniformly almost everywhere. Right? Because, well, let's draw again here the graph of the function. So these are function xn. They are converging to 0, but the convergence will not be uniform in any interval containing, open interval containing 1, so you can't expect to have uniform convergence, almost surely. Right? So to have uniform convergence, you need to remove an interval which has positive measure. You're not able to remove a set of measures 0 and get uniform convergence, because if you remove a set of measures 0, you'll always have points converging to 1, and therefore you won't have uniform convergence on that set. So this is an example of a sequence of functions which converge almost everywhere, but which do not converge uniformly almost everywhere. And it's in view of this example that we will introduce the third concept of convergence, which is almost sure uniform convergence, which I will now define. So the last concept of this lecture will be convergence which is almost uniform, or almost uniform convergence. And this is exactly inspired by the example we just have seen. We have seen that if we want to have uniform convergence in that example, we have to remove a set of positive measure. But the measure of the set removed can be as small as 1 wants. So we will say that, again, we have a sequence. So this is the third definition. We have functions defined on omega taking a value on r bar, and we will say that fn converge to f almost uniformly if for every epsilon I can find a set E epsilon in the sigma algebra F such that mu of E epsilon complement it's smaller than epsilon. So now I'm not requiring anymore the set to have measure 0, but I'm asking it to have measure bounded by epsilon, and Fn converge to F uniformly on epsilon. And and this is tailor made in order to include the previous example. So again, let's consider the functions x to the power n. Now if you fix an epsilon positive, I can just remove from my set the interval 1 minus epsilon 1. So let me call that E epsilon complement. Of course, the Lebesgue measure of this set, it's equal to epsilon. And on the set 0, 1 minus epsilon, the function fn converge uniformly to 0. So this is a third concept to take care of this type of example. So what we do is what we need to show is that whatever epsilon you are given, you can remove a set of measure smaller than epsilon, and to show that in the complement of this set you have uniform convergence. Well, let's compare a bit all these three concepts. So we have Fn converging to F almost everywhere, Fn converging to F uniformly almost everywhere, and Fn converging to F almost uniformly. Right, well, it's clear that this second condition is stronger than both. So it implies both. It's stronger. If you have uniform almost everywhere convergence, well, outside the set of measures, 0, you have uniform convergence, so that you have almost sure convergence, and you have almost uniform convergence. So this one, it's clearly the strongest one. Now, what I claim is that, well, you have, if you converge almost uniformly, you converge almost everywhere. So let me use this piece of the blackboard in order to prove that. So let's assume that Fn is converging to F almost uniformly. This means that for any n, for any k, you can find a set Ek such that Fn converge to F uniformly on Ek, and the measure of Ek complement, it's bounded by 1 over k. Right? So for any k, 1 over k you give me, I can find a set Ek whose complement has measure bounded by 1 over k, and you have convergence on Ek. So if I have uniform convergence on Ek, I have also pointwise convergence on Ek. That's clear. So now if I take the intersection of all Ek complement, the measure of this intersection, it's of course bounded by the measure of Ek0 complement. So this is true for any k0, and this is bounded by 1 over k, 0. Since this is true for any k0, this means that the measure of this set is equal to 0. On the other hand, if I take the complement of this set, this is the union over k of Ek. So let me call this set E. We just proved that E complement has measure 0. And on the set E, what I claim is that I have pointwise convergence. Because take a point x in E, this means that it belongs to one of these Ek, and I have pointwise convergence on Ek. So I have that Fnx converge to Fx for all x in E. And therefore, and this is exactly almost sure convergence of Fn to F. So this proves that if Fn is converging to F almost uniformly, it converges to F almost everywhere. What is surprising is that if the measure of our set omega is finite, then the complement, so the converse statement also hold. And this is what I want to prove. So what I want to prove is that if now we assume that the set omega has finite measure, then almost sure convergence implies almost uniform convergence. And this is somehow surprising, right? That, well, you are starting from a sequence which converges pointwisely at almost every point. And from this information, you can deduce that, in fact, if you are allowed to remove a set of measure epsilon, then you get uniform convergence. So this is our last claim of today's lecture, which I will present now. So let's state the theorem, which is due to Egorov. So assume that the measure of the set omega it's finite, and let's consider sequence Fn which is converging to F almost surely. Then what we claim is that Fn it's in fact converging to F almost uniformly. So for the proof, what we want to transform in terms of sets, it's the assertion that Fn of x is converging to F of x. Well, what does that mean? That means that for any k, so if I observe the points x such that Fl of x minus F of x, saying that Fl of x is converging to F of x means that for any epsilon, I can find n such that for all L larger than n, this difference is bounded by epsilon. As epsilon, we will use 1 over k, so we want this to be bounded by 1 over k. And now so saying that this sequence is converging means that for all k, we can find some n such that for all L larger than k, this difference is bounded by 1 over k. This means, this translates into sets, the concept of convergence of this sequence Flx to Fx. And so so this is the set of points x for which Fn of x converge to F of x. Since by assumption this convergence is almost sure, this means that the complement of this set has measure 0. So the assumption is that the measure of the complement of this set it's equal to 0. Right? As I said, this set represents the set of points x for which Fl of x converge to Fx, and therefore saying that this convergence holds almost everywhere means that the complement of this set has measure 0. This is just what we wrote. So now, let's compute what's let's calculate the complement of this set. The complement of this set is the union of the intersection of the union of the complement of this set, which is all points x, such that Flx minus Fx it's greater than 1 over k. And this set has measure 0. So maybe let's continue in the other blackboard. So keep in mind this identity, and so let me just explain what I will write next. So the measure of this set it's equal to 0, but this is a union. So for this union to have measure 0, this means that for all k, this set has sorry, this is not k, this is n. For all L larger than n, right? Please check that. So now let's go back to this equation, saying that the measure of this set is equal to 0. Since this is a union, this means that for all k, the measure of this set is equal to 0. And this is what I will write next. Just proved that for all k, the measure of the intersection over all n larger than 1, the union over all n larger than n of the points x such that fl of x minus fx, it's larger than 1 over k, that this has measure 0. Okay? So this is what I claimed. We had here union over all k. Since the measure of the union was 0, this was equivalent to say that for all k, this measure is equal to 0. Now, let's observe what we have here. Let me call this set here. K it's fixed, so let's forget this dependence on k. So let me call this set an. What I claim is that this is a decreasing sequence of sets. So let's compare an with the set an plus 1. So the set an plus 1 means that this union is starting at n plus 1. This means that an it's equal to an plus 1 union the set in which I take L equal to n, which means that an contains an plus 1, so that an it's a decreasing sequence, and an decreases to the intersection over all a's. And at this point, we will use our assumption that the set has finite measure. Since the set has finite measure, we can use the continuity from above of the measure to say that the measure of an it's converging to the measure of the intersection. What we have here is the intersection. Therefore, by the continuity, what we get is that the measure of an is converging to the measure of the intersection, which is equal to 0, which means that for all k, the measure of the set an, which is L larger than n of all points x such that f of Lx minus fx larger than 1 over k, that this set it's converging to 0. So that the limit in n of this measure it's equal to 0. And this is for all k. Okay, now we will use this information in order to construct a set which has measure at least epsilon, and so that in the complement of this set we have uniform convergence. So let's fix epsilon positive, and so this is true for all k, so which means that we can find n, which depends on epsilon and k, for which this measure it's bounded by epsilon divided by, say, 2 over k, 2 at the power k. So what I claim is that this holds for all k. So let's fix 1k and 1 epsilon. Since this holds for all k, we can find n, which depends on epsilon and k, such that the measure of this set it's bounded by, say, epsilon divided by 2k for all n larger than nk epsilon. So let me write that properly. So we know that there exists n epsilon k, such that for all n larger than n epsilon k, the measure of this set, L larger than n, of x such that f L x minus fx larger than 1 over k, that this is less or equal than epsilon divided by 2k. Okay? So we fixed epsilon divided by 2k. Since this limit is 0, we can find n such that for which this is true. So since this is true for all n larger than n epsilon k, this is true for n equal n epsilon k. So we have that inequality. Up to this point, we reach this fact that for any epsilon, we can find this n for which this is true. So let me erase in order to continue in the same blackboard. We are almost at the end of the proof. So this set has measure less than epsilon to the 2k. Let's take the union over all k. So let's take the union over all k larger than 1, union over all epsilon larger than n epsilon k of x such that flx minus fx larger than 1 over k. So the measure of this set, it's less than or equal than the sum over k of this, the measure of these sets. The measure of these sets, it's bounded by epsilon to the 2k. So when we sum over k, we get that this is bounded by epsilon. Okay. So we obtained in this way a set whose measure it's bounded by epsilon. So this will be the set E epsilon complement. We just proved that this set E epsilon complement has measure bounded by epsilon. So now let's see what is the set E epsilon. Well, the set E epsilon is the set, well, the complement of this set, which means that the intersection over all k, intersection over all L larger than n epsilon k of the points x such that flx minus fx it's less or equal than 1 over k. And we have to prove, in order to complete the proof, we have to show that we have uniform convergence of fl to f in this set E epsilon, right? Because if we prove that, we have proved almost uniform convergence because epsilon is general. For that fixed epsilon, we obtain the set E epsilon, such that the complement of E epsilon has measure bounded by epsilon, and we have uniform convergence on E epsilon. So what remains to be shown is that on this set we have uniform convergence. And this is what I'm going to show now. Well, to show that you have uniform convergence, fix some delta positive, we have to find a certain m, which depends on this delta, such that for all n larger than m delta, this difference is bounded by delta. So fix delta. Well, if you fix delta, you can find a k such that 1 over k it's smaller than this delta. Fix that k and fix, so for that given k you have n, which depends on epsilon and k. So fix an L larger than n epsilon k. For this L, flx minus fx, it's bounded by 1 over k, but 1 over k it's bounded by delta. So what I claim is that the supremum for x in E of flx minus fx, it's bounded by delta for all L larger than n e k, epsilon k. Okay, why this is true? Well, take a point x in E, epsilon, take a point x in E epsilon. So it belongs to all this intersection. So it belongs to this set for all k. Since it belongs to this set for all k, it belongs to this set for all L larger than n epsilon k. So it belongs to this set which depends on L for all L larger than n epsilon k. Which means that if I take L larger than n epsilon k, since it belongs to this set, this difference, it's bounded by 1 over k, but 1 over k is bounded by delta. So this proves that indeed, for all L larger than n epsilon k, this supremum is bounded by delta, and this proves uniform convergence on E epsilon, right? If we set m delta to be equal to this n epsilon 1 over k, or k, we have that for all L larger than m delta, this supremum is bounded by delta, so that we have uniform convergence on the set E epsilon, which proves that the sequence FL almost uniformly converge to F. And this is the last result I wanted to prove in this section.